So the rule of restricting science to laws about phenomena and rejecting laws about laws is untenable. Note that that rule is itself a principle, the anti-principle principle. And as we've just seen, it's false. More generally, I think the whole purpose of theoretical science is to explain the world, the physical world, and therefore the sole criterion by which theories ought to be judged is their explanatory power. This rules out having preferences between modes of explanation, preferences that, if those preferences are independent of how good the explanations are, that should be what counts, the only thing that counts. So, just as a scientific theory about phenomena is much more than just an instrument of prediction of those phenomena, much more than just a compressed summary of them, but is an explanation of them. So a principle of nature is not just a statement of shared properties among theories. It is an explanation of those properties. Now, the prevailing conception is a principle too, isn't it? And I believe it's just as false, as I'll explain in a moment. So, what other principles of nature might be true aside from those of thermodynamics that I've mentioned? Well, both quantum theory and relativity are partly principles. In addition to making direct predictions about phenomena, they also assert that all other laws of nature, including each other, conform to certain principles, such as the principle that laws are formulated in terms of geometrical objects, in the case of general relativity, and in quantum theory, the principle of unitarity. And as those two examples illustrate, we shouldn't expect there to be a rigid hierarchy of principles, with ordinary laws being subordinate to principles, but we should expect that the immense explanatory power of some of our theories, of our best theories, implies that if they are true of some physical systems, they must be true of all of them. I think it was Feynman who called this, in the case of quantum theory, the totalitarian property of quantum theory, which I think Bryce DeWitt proved the same thing, and I think independently, that if any system in the universe is governed by quantum theory, then no system that could interact with that one could obey classical laws of motion. Relativity isn't quite as totalitarian as quantum theory, but its principles do seem to be inconsistent with those of quantum theory, so presumably one or both of them must be superseded. Something that we couldn't know unless we regarded those two theories as principles. Now, for example, they might just apply to different phenomena. Now, the way in which DeWitt, in particular, proved the totalitarian property, I'm not sure how Feynman did it, is quite significant from my present perspective. He used the so-called uncertainty principle of quantum mechanics, horribly misnamed, and he assumed for the sake of argument that it did only apply to quantum systems, and that classical objects could exist in nature too, and could interact with some quantum system. And then he showed by an ingenious set of arguments that by making certain measurements, one could violate the uncertainty principle, not just for the combined system, but even within the quantum system. So loosely speaking, quantum theory either applies to everything or to nothing. And the reason that that mode of proof is significant to me now is that it uses the uncertainty principle in the form such and such a class of tasks is impossible. And if a certain physical object is possible, the classical object, then a further process would be possible that would lead to a contradiction. And therefore, if the principle is true, the classical object isn't possible. He expressed the proof in the prevailing conception, but it's barely used as such. You see, saying that a given task is impossible in the sense that the uncertainty principle does means that it, not just that it doesn't happen, but that it can't be caused to happen by anything. Can't be caused with the help of anything else. Even things not explicitly referred to, things not yet known. And that's the core of the totalitarian proof. So a while ago, I proposed a new mode of explanation that Philip referred to, of constructor theory, or rather a theory called constructor theory, which I hope will incorporate this new mode of explanation, which is intended eventually to supersede the prevailing conception, though the two are intertranslatable in many cases. The first principle of constructor theory is this: the laws of physics are expressible entirely in terms of statements about which physical transformations it's possible to cause to happen and which are impossible to cause, and why. So this is about transformations that are caused by something, some agent which is itself not specified, that any agent, except that this agent must itself be possible. And there's a condition that the agent retain its ability to cause the transformation again. Otherwise, it's only partly an agent and partly a patient. A chemical catalyst is an example of such an agent. It causes chemical reactions but does not participate in them. By the way, we're told in elementary chemistry classes that it doesn't cause chemical reactions, it just changes their speed, but that is not the case. So the heat engine is also such an agent. It converts things to have different temperatures and so on, but it itself stays the same. So is a computer. We call these agents generically constructors. And by possible to cause, we mean possible with arbitrary accuracy. That is, you give me an epsilon, and if a task is possible, you give me an epsilon, and someone could design a constructor which causes that task to happen with accuracy, epsilon or better. And impossible means that the laws of physics exclude the possibility that anyone could ever produce such a design, or the laws of physics rule out the existence of such an agent, such a constructor. So there are no probabilities in the constructor-theoretic conception of the world. Tasks that look probabilistic, like building a fair roulette wheel, are expressed in terms of preparing it in a specified quantum mechanical state with a given density matrix, for example. So, while the prevailing conception seeks to distinguish at a fundamental level what happens from what doesn't happen, in which case possible and impossible are just a manner of speaking about certain approximations or about our ignorance. But in constructor theory, it's the other way around. The laws of nature are about what's possible and impossible, in the sense I've just described. And what actually happens is, in general, an emergent consequence of that. Sometimes it can be calculated, in which case the constructor theory and the prevailing conception are equivalent. But sometimes it can't be calculated, either because it's intractable or for some more profound reason. And in those cases, constructor theory can express exact laws that are inaccessible in the prevailing conception. One important case of the latter are initial conditions of the universe. They are, in constructor theory, they are supposed to be incalculable consequences of laws about what's possible and what's impossible. And that is so reasonable. As I said, you wouldn't expect there to be a fundamental law specifying the state at any other time than the initial time, such as today, including all the locations of all the cows in Oxfordshire that were auctioned today. You wouldn't expect the state of those cows to have fundamental significance. Why expect it of the initial state? Especially as this violates symmetries that exist everywhere else in physics. And with that constructor theoretic perspective, we can begin to notice that there are already other principles of nature that are already known, but are not usually acknowledged as such, nor even acknowledged as being part of physics at all, simply because they don't conform to the prevailing conception. There's the principles of the theory of computation, for example. The distinction between computable and non-computable functions doesn't refer to what the computer is made of. We expect it to be the same for any make or model or technology of general purpose computer, even ones using laws of physics or materials not yet discovered. So it's a principle, difficult or impossible to express in the prevailing conception. But in some work that my colleague Chiara Marletto and I have done, we have shown that there is a beautiful expression of this principle in constructor theory. And this is in the context of a full constructor theoretic information theory in which processes like computation and quantities like information are characterized in elegant, exact terms. That is, in constructor theoretic terms, in terms of what classes of physical transformation it's possible or impossible to cause. This new theory of information, which I commend to you all, unlike Shannon's existing theory, naturally includes quantum information and predicts all its strange and distinctive properties, such as the impossibility of cloning, the information in a quantum state, and the famous unpredictability of quantum measurement, despite its deterministic law of motion. And Marletto has also used constructor theory in a biological application to characterize what precisely it is about the laws of physics that permits the origin and evolution of life. Among other things, the apparently non-physics concept of the appearance of design, which was coined, I think, by Richard Dawkins, has an exact definition in constructor theoretic physics. The result is that regardless of the so-called fine-tuning coincidences in the constants of physics, the laws of physics do not in fact have to have, and do not in fact have, the appearance of design for causing life.